Since we now know how to identify molecules and we know how they interact with each other, we can now look at what makes these particles interact in the ways they do. And we'll start by focusing on gases. And the main way that we look at how particles move is using the kinetic molecular theory. And let's try to figure out what this theory actually means. Well, kinetic. What does kinetic mean? It reminds you of kinetic energy. Kinetic means movement. Okay, so we have movement, and then we have molecular. So molecular refers to molecules. So the kinetic molecular theory describes the movement of particles. And remember, particles can be atoms, they can be molecules. And when we describe the movement of particles, there are a few assumptions that we state. And assumptions are just things that we say in order to make a theory easier to use to make predictions. Assumptions are ways of simplifying a very complicated problem. So let's look at what particles do in a substance. So this movie is from PATT, and it shows the movement of particles in a closed container. And what can we learn about these particles? Well, we see that these particles are really, really small compared to the total size of the container. We also see that they move randomly. You don't see all of the particles moving one way or the other way. They're bouncing all over the place. In connection to that, they're bouncing off each other. The molecules bounce off, and they bounce off the walls. And you can also see, are all molecules moving at the same speed? Well, let's look closely again. So this time watch and tell me if all molecules are moving at the same speed. If you look, they change speeds in here, but overall they seem to be moving at a constant rate, with a few of them moving faster and a few moving slower. So using this model, let's see what some assumptions, some simplifications are in the kinetic molecular theory. The first part of this kinetic molecular theory is that particles are very small compared to the volume of the container. Another way to say this is that the particles don't take up much space, which is true. Molecules and atoms are really, really, really small compared to the size of the container. That simulation is actually showing the particles even bigger than they would be. So particles are very, very small. The second part of this is particles move randomly and are constantly moving. So these particles are moving around, they're bouncing around, and there's no one direction that they have. So they're all moving randomly about the container. The third part is all collisions are elastic. And an elastic collision is just that energy is conserved. So when two particles bump into each other, think of a really bouncy ball. If I throw a bouncy ball against the wall, it bounces back just as fast as I threw it at the wall. But if I threw a bowling ball at the wall, that would stop. So we think about these particles as bouncy balls. They bounce off each other, and the total energy doesn't change. The fourth assumption is that there are no intermolecular, attractive, or repulsive forces in between the particles. So as you watch the video, you see that the particles are moving all over, but they're not attracted to one another. If they were all attracted, you would see them all kind of clump up. And they don't repel each other. They don't stay away from each other. So there are no intermolecular attractive or repulsive forces between these particles. And the fifth and final part of this is that temperature is related to the average kinetic energy of the particles. And really all this is saying is that the faster the particles move, the higher the temperature. And then vice versa. The slower they move, the lower the temperature.